Hello. So I guess we're going to start the next section, which has to do with related rates. And so these are going to be applications of what we've been doing, namely taking derivatives. And again, the word rate, right, implies rate of change, which means derivative, right? And so here's some guidelines, just some things to think about when you're solving these types of questions. The first, obviously, is just to make sure you read and understand what the problem is asking and identify what's given, right, or what is known in the problem, and then what are the unknown quantities? What are we looking for, right? Make a sketch or a picture if you want, and then label all the quantities. And I've noticed in the book, they like to give you the picture, and in fact, they usually label most of the quantities already. So some of this you don't have to do. But in some problems, they won't give you the picture, and in that case, you should probably draw it yourself. Right, so then the next step is to write an equation that involves all the quantities given. And this very often will involve geometry, right? So you might be talking about spheres or cylinders or cones, or in some cases just two-dimensional pictures like circles, discs, or triangles. And if you look in the back of the book, there's a whole page of formulas from geometry. And so, again, some of those you should know, but if not, you can always look them up. So, once you have that equation, again, that usually comes from geometry, although not in every case, right? Then, using the chain rule, you're going to take the derivative implicitly, right? So, it depends on the equation, of course. If the equation is given explicitly, then you're taking the explicit derivative. But in most cases, you're taking the derivative implicitly. And again, don't forget to use the chain rule. The chain rule here is the key. And because we're changing over time, the variable we're taking the derivative with respect to is going to be time here, right? In most cases, I would say. And then when you solve for the derivative, right, solve for the derivative, and then when you substitute all the given quantities, that should answer the question, and then just make sure you answer the correct question, what they're asking for, right? All right, so with that, let's just go on to the first example, which really, the equation is given, so there's nothing to really, there's no pictures here. So this should be pretty straightforward, right? The equation is, and let me just copy it down here. So this is example 1. The equation is x squared plus y to the 4th is equal to 25. And we're given the following information, that the derivative of x with respect to t is 48. And we want to find the derivative of y with respect to t for x equals 3 and y equals 2. Okay, so yeah, the one thing you don't want to do right now is plug in x equals 3 and y equals 2. You'll just get 25 equals 25, right? So we're going to leave the equation alone, and then to find the derivatives, the rate of change, we will just take the derivative of both sides, right? So this will be implicit differentiation, as I explained earlier. Usually you're going to be doing this implicitly, although not always. Okay, so far? So, yep, taking the derivative here. On the left side, we'll just use the sum rule, right? So the derivative of x squared is not 2x. Why not? Well, because we're taking the derivative with respect to t. And maybe I'll write this out one last time. So using the sum rule, we're taking the derivative of x squared plus the derivative of y to the 4th. But notice it's with respect to t, right? Okay. And then on the right side, the derivative of 25 is 0. That's it. Try that again. There we go. Right, so yeah, the derivative of x squared is not 2x, right? It's going to be 2x times the derivative of x, right? Again, that's the chain rule in step 3 here. So don't forget the chain rule, right? Same thing here. This is not 4y cubed, but rather 4y cubed times the derivative of y with respect to t. And that's still equal to 0. Right? So what are we looking for here? We're looking for dy by dt. So we want to solve for this quantity here. And that's just algebra. So we can subtract the 2x dx over dt from both sides. We get 4y cubed times the derivative of y. And that has to equal negative 2x times the derivative of x. Right. And then just divide both sides by 4y cubed. And then we'll go up here. So, so these cancel, and so the derivative of y with respect to t is going to be negative 2x over 4y cubed times the derivative of y. And of course we can cancel the 2's here, so this is just negative x over 2y cubed times the derivative of y. Oh, sorry, the derivative of x. Yeah. Phew, yeah. So these are x's here. That, and that's an x. Right, so yeah, we're solving for the derivative of y. That's on the left side of the equation. Right. You should be x's. Same thing here, right? Okay, great. So now we just plug in the numbers, right? So the derivative of y with respect to t will equal, again, I'm going to plug it into this because we already got rid of the 2's here. So what is x? X is 3 divided by 2y cubed. So that's 2 times 2 cubed. And then the derivative of x was 48. So this is all times 48. So yeah, let's see. So this will be negative 3 times 48 divided by 2 to the 4th is 16. Yep, 2 times 8, 16. And 48 divided by 16 is 3. So negative 3 times 3 is negative 9. And that's the answer, right? So the derivative of y with respect to t, that was what we were looking for here. Well, here. So I'll write the answer in yellow. So the derivative of y with respect to t is just negative 9. And again, we didn't provide units here. We didn't say, y is in feet or meters or inches or centimeters. So these are just pure numbers at this point. Okay. So that's how it works when you're just given the equation. You're given, one of the rates, and you have to find the other rates, the rate of y in terms of the rate of x. Okay. The rate of change of y in terms of the rate of change of x, right? And that's usually how this is going to go when the equation might not be given. Okay, so let's look at one of those now. Okay, so I just pulled this one out of our book. It's number 16. So it's an even one, so it's probably one that's not for homework. And the question has to do with surface area. All edges of a cube. So you know what a cube is, right? Try to draw a cube. Let's try that again. All right, close enough, right? So all edges of a cube, and so all edges are the same. So we can call it x, then this side is x, then this side is x, right? So all edges of the cube are expanding at a rate, right? So the key word here is expanding at a rate of 6 centimeters per second. So the cube is getting bigger, right? So sometime later, the cube will be bigger It'll look something like this, right? And so x is changing, x is getting bigger, right? It won't be the same value as it is here. Right. So again, the key word is rate, right? And so this is the derivative. What is it the derivative of? The edge of the cube, x. So it's the derivative of x with respect to t. This is given as 6 centimeters per second. Okay, so this is given. This is part of the problem. Okay. And so the question is, how fast is the surface area changing when each edge is, and then there's two parts to this. Part A, when x is 2 centimeters. So let's write that down. So what are we looking for? We're looking for the rate of change of the area, the surface area of the cube, for x is equal to 2 centimeters. And then part B, again, we want to find the same rate of change of the area of the cube for x is equal to 10 centimeters. So we're just plugging in different numbers, right? Okay. So most of the problem has to do with how do you find the surface area of a cube? Well, what is a cube but 6 sides, right? Here's the front of the cube. And that side, well, it's a square, right? How do you find the area of a square? Length times width. Both are x, so that area is x squared, right? Well, but there's 6 sides, right? There's the front, there's the back, which is way back over here. There's the top and the bottom, and then there's the right and the left. So there are 6 sides, right? So each of them is a square of area x squared. So to get the total area, you just multiply 6 times x squared, right? So the surface area is just 6x squared. Okay? Right. So what are we looking for? We're looking for the derivative of a. Right? So that's going to be the derivative of 6x squared. Right? The 6 is a constant. That can come outside. Although you can do that in your head, right? And then you just take the derivative of x squared, which is 2x. Right? Good. Of course not. Right? This won't answer the question because we want the derivative with respect to t, not with respect to x. So again, what are we missing? Chain rule, right? We need to multiply by the derivative of x with respect to t. Chain rule, number 3 here, right? Very important. Okay, so that should do it. 6 times 2x is 12x, so 12x times the derivative of x. Right? And so that gives us the derivative of the surface area. Now we can just plug in the numbers for part A. Right? We can also write a prime of t, that's fine too, for the derivative. So 12 times x, well what's x? In part A, x is 2, so 2 centimeters. And then what's the derivative of x with respect to t? That was given, right? That was 6 centimeters per second. So 6 centimeters per second, right? And so now we get 12 times 2 times 6. That's 12 times 12, so I think we get 144. And let's note the units, right? We have centimeters times centimeters, so that's going to be square centimeters over seconds. So that's an area, right? That's an area divided by time. Square centimeters per second. So I think we have the correct units. And that should answer part A. The surface area is increasing at a rate of 144 square centimeters per second. And again, part B, well, I should let you do that, but it's the same thing, right? So we still have the derivative is 12x times the derivative of x. So now you're just plugging in x equals 10 instead of 2. So it's now 12 times 10 centimeters, and then the derivative of x is still 6 centimeters per second. Don't quote me on this yet. I think it's 720 square centimeters per second. So yeah, 12 times 6 is 72. And 72 times 10, yeah, 720 square centimeters per second. So that's part B. Okay, so that's how that goes. So yeah, there's a little bit of geometry here. You have to know surface area of a cube, right? I think the one you're going to do for homework has to do with the volume of a cube. And you should know the volume is just x times x times x, or x cubed. Right? So that'll be in cubic centimeters for volume. Right? Okay, let's do a slightly harder one. Okay, so this is number 19 from the book. And, you know, it's one for homework. It's one that you really should try first because it probably is in the homework. I'm not sure if it's on WebAssign or not, but it's maybe a similar one. So I know this is a little bit smaller, so I'll read the question. It says, a swimming pool is 12 meters long, 6 meters wide, and 1 meter deep at the shallow end. So yeah, this is the shallow end over here, right? So that's 1 meter deep, and it's 3 meters deep at the deep end, which is over here, right? So here's the shallow end, here's the deep end. And water is being pumped into the pool at 1/4 cubic meter per minute, and there is 1 meter of water at the deep end. Okay, so there, again, they give you the picture here, and I kind of ruined it, but there's the picture. And so there's two questions. First, what percent of the pool is filled? And part B, at what rate is the water level rising? Okay, so let's start with the first question. And yeah, so for part A, here's what I would recommend, right? Notice that the width of the pool, 6 meters here, is a constant. That does not change. If you look straight down at the pool, it's just a rectangle. And the width is 6 meters. Okay, so that's not changing. Okay, so what I'm telling you is you can look at the pool from the side. And if you look at it from the side, it looks something like this. Okay? Yep. And so, again, just to illustrate the point here, this is 1 meter deep at the shallow end, and this is 1, 2, 3 meters deep at the deep end. And right now, there is 1 meter of water at the deep end. So this is your 1 meter here, and then all of this is just water. So fill that in with water. There we go, right? So what percent of the entire pool is filled with water? So this really has nothing to do with calculus. This is a geometry problem or an algebra problem, and it's a good review though, right? And here's what we want. We want the ratio. So for part A, we want the ratio of the volume of water divided by the volume of the entire pool. Okay, that's the ratio we want, right? And that'll give us, when we divide them, it'll give us a fraction, but we can multiply by 100 to get the percent, right? So what's the volume of water here? Well, looking at it from the side, it looks like area, right? It's a triangle. And you know the area of a triangle, right? It's just 1/2 the base times the height. So the height, remember, was 1 meter here. And what's the base? What's the length of this from here to here? So get rid of that little arrow here. Well, so notice that this is, if the water were this deep, oops, I messed that up. If the water were this deep, it would be 2 meters deep. And I think I forgot to tell you the length of the pool. It's 12 meters, right? So from here to here, it's 12 meters. It's 12 meters long. So what you get is rise over run, right? You get a triangle that's 2 meters high and 12 meters long, right? Now, if you're thinking, wait a minute, it's 3 meters high, that's true, but we're not going from here to here, right? We're only going to the shallow end, which is 1 meter deep. So 3 minus 1 is 2. So this part here, right, that's the 2 meters. Okay, so rise over run is 2 over 12, or 1 over 6. So for 1 meter deep, right, this length here is just half of that. It's 6 meters. So 1/2 the base is 6 meters, and the height is 1 meter, so the area is 3 square meters. Right? So that's the area for the water. Now what about the area for the entire pool? Right, so for the whole pool. Well, let's see, we have this triangular part here, which I drew here, and that's still a triangle. In this case, the area is 1/2 the base times the height, which is 1/2, the base is now 12, and the height is 2. So I think that's 6 times 2 is 12. So 12 square meters. But notice, that's only part of the pool. There's also this part up here, and that's just a rectangle. The length is 12, the height is 1, so that's also 12 square meters. So, right, so this is plus the length times the height. And so, yeah, I'll just copy this down, right? So it's 12 square meters for the triangular part, and then it's also 12 square meters for the rectangular part. And so that gives us a total of 24 square meters. Okay. Now, right, remember I said we want the volume of water, not the area. It doesn't matter. You can use the areas as well. So how would we get the volume? So going back to first part here, right? So the volume of water divided by the volume of the pool. So in the picture here, we got the area, and now we just have to multiply by the width to get the volume. But the width is the same for all of this. It's 6 meters, right? So to get the volume of water, it's going to be 3 square meters for the area times 6 meters for the width. For the volume of the pool, it's going to be 24 square meters times 6 meters for the width. And you can see, that's why I said the volume doesn't matter. You can just find the area because the 6's cancel. And then, of course, 3 over 24 is 1 over 8. So that's the ratio, right? 1/8 of the pool is filled. The pool is filled with water. Okay. Now, of course, maybe they're being picky here, but they want the percent. So you know how to convert a fraction to a percent. It's 12.5%, right? So in other words, 1 over 8 is 0.125. So final answer, 12.5% of the pool is filled with water. And notice there was no derivatives in this at all. We didn't take any derivatives. This is all just, the area of a triangle, right? Or the area of a rectangle, and then just adding them up. Okay, so that's part A. Really just a good review question. Do you understand how to find areas and volumes and things like that? Right, so now let's get to the calculus part. That's going to be part B here. Right, at what rate is the water level rising? So yeah, the key word here is rate. When they say rate, they mean rate of change. What they mean is the derivative. So at what rate is the water level rising? So the water level, right, is going up. So that's increasing in height. So we want to find the rate of change of the height or the derivative of the height. Okay. So let me just sort of copy down the side of the pool. Looking at it from the side again, we have this picture here. Right. And then this is the rectangular part at the top. But notice the water level is only 1 meter deep. So again, here's the water. Fill that in. And as the pool is filling up, right, the water level is rising. And so we'll call this the height, h. Now, of course, at this moment, the height is 1 meter. But if you wait just a second later, the height will be a little bit bigger than 1 meter, a little bit higher than 1 meter, right? Because it's filling up. So the height is a variable. It is changing. Okay. In part A, we didn't care about that. We took our snapshot. We took our picture. At that moment, it looks like we have a certain amount of water in the pool, right? But because you can see over here, right, we are filling the pool with water. And so the water level is rising. So what is the rate of change of the height? Okay. Well, what are we given? Right, we're given this picture. And we're also given, way over here, that water is being pumped into the pool at 1/4 cubic meter per minute. So cubic meter is a volume. I don't have enough space here, right? So what we are given is the rate, oops, can't see that. We are given the rate of change of volume is 1/4 cubic meter per, I think it was minute. So I can't use m for minute because we use m for meter. Yep, 1/4 cubic meter per minute. And that is the rate, that's how quickly we're filling up the water, right? 1/4 of a cubic meter every minute goes into the pool. Okay. Right. So yeah, what are we trying to solve for? We're trying to solve for the derivative of h when we have the derivative of v. Right? So the question is, right, how are v and h related? Right? What's the relationship between the volume and the height? So the volume, remember, is the volume of water here. So it's the area of the triangle times 6, right? 6 meters, because remember it's 6 meters wide. Right? And what's the area of this triangle? Well, the area is just 1/2 the base times the height. Right? The base being this distance here, right? Which at the moment, right, is 6 meters, but again, as the water level's changing, that's going to be increasing. So h is not a constant and b is not a constant here. On the other hand, what's the relationship between b and h? So we'll pull this up here, remember. So the two triangles, right, are similar triangles here. This triangle here and the blue triangle. right? One is bigger than the other, but the ratio of the height and the length are the same. 2 to 12 or 1 to 6, right? So in other words, right, the height over the base, which we can also call the length, so h over b is just 2 over 12 or 1 over 6. Right? So h divided by b is just 1 over 6. Oops, that's a 6, not a b. Right? So multiply by b, and you get h is b over 6. B divided by 6. And we can solve for b by multiplying by 6. So b is just 6 times h. Right? And then I can plug that in here to get the area in terms of h. We know b is 6 times h, and then times h. Right? So half of 6 is 3, and h times h is h squared. So the area is 3h squared. And so now the volume is the area, 3h squared, right, times the 6 meters, right, times the 6 meters, and that's the depth. I'm sorry, the width of the pool is 6 meters. And that was a constant, right? So it looks like for the volume, we get 3 times 6h squared, 18h squared. And so that answers the question, how are v and h related? V is 18 times h squared. Everyone got that? So I hope that makes sense. Again, that's just geometry. It's just area of a triangle, and then area times the width gives you the volume. Okay, so we have v. Now we just need the derivative of v, right? So all of this was just geometry and algebra. Now comes the calculus. Now we take the derivative of v, right? And you can say this is explicit differentiation because it's just the derivative of v, right? The 18 is a constant, and the derivative of h squared is not 2h, right? Remember chain rule here. 2h times the derivative of h. Right. After all, this is what we're looking for. So if you forget the chain rule, right, and you just write this as 36 times h, well, great. But that doesn't answer the question. The question is, what is the derivative of h? So if you forget the derivative of h by forgetting the chain rule, you're not going to be able to answer the question. Makes sense? So, sorry, that's an h. Looks like a b here. Right. And so we get our equation. Notice that the left-hand side, right, is just equal to 1/4. I don't know why I switched to green there, but that was the given part, right, is 1/4. And that's equal to 36 times h times the derivative of h. Okay, so now you're just solving for the derivative of h, so we can divide both sides by 36h. So 1 over 36 times h. And so the derivative of h with respect to t is just going to be 1 over, let's see, 36 times 4. I want to say 144 times h. Yep, I just wanted to double check that. So yeah, 1 over 44 times h. And now we just plug in the numbers, right? So when h is what? Well, when h is 1 meter, right? Because that's right there. And there is 1 meter of water at the deep end. There is 1 meter of water at the deep end. See that? So h is 1. And if h is 1, then this, right, so we'll plug in at h equals 1. This is 1 over 144 times 1, or just 1 over 144. So remember, h is in meters, and t is in, I was going to say seconds, but I think it's minutes, right? Yes, minutes. So 1 over 144 meters per minute. And I think that answers the question, right? The question was to find the derivative of h Derivative of h with respect to t. How fast is the water level rising? Oops. Well, not very fast, right? 1 over 144 is a pretty small number. So the water level is not rising all that quickly. But then again, the volume is not increasing that quickly either. 1/4 cubic meter per minute. Well, a cubic meter is actually a very big volume, so it's maybe a little bit faster than it looks. Right, so that should do it for part B. Remember, part A was just what's the percent, and that's the 12.5%. And at what rate is the water level rising? 1 over 144 meters per minute. Okay, so I hope that helps. Again, it's a very good problem, but it's a lot of geometry here. It's a lot of, triangles and well, I guess when you consider the volume, it would be like a wedge. It's a wedge-shaped object here, right? Okay. What would make this a little more confusing is if the water level, instead of being 1 meter, let's say it's 2.5 meters. Now the water is all the way to the shallow end. And you can see now you have to combine the triangular part with this little rectangular part. And that would make it a little trickier, but they didn't do that. So that was number 19. I hope this helps, and we'll just go on to another one. Okay, so on to the next one. This has to do with a ladder leaning against the side of a house. It says a ladder 25 feet long is leaning against the wall of a house. Here's the picture in the book. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. Right, and so so there's a little arrow indicating that the ladder is being pulled away from the wall. And so you know what happens if you pull the ladder away from the wall, then the top of the ladder up here is going to move down the wall. And I think we sort of seen that before in one of the problems in chapter 1 having to do with limits, right? So, yeah, but this one's going to be a little bit different. It's still concerned with how quickly is the ladder moving down the wall, right? And so part A, how fast is the top of the ladder moving down the wall when its base is 7 feet, 15 feet, and 24 feet from the wall? So we want to plug in 3 different numbers here, 7, 15, and 24. Okay, so what is the base of the ladder here, right, is how far from the wall? Here's the wall. Well, as we're pulling the ladder away from the wall, you notice that distance is changing. So maybe we should call it x, right? Okay, and how high is the ladder from the ground? Well, why don't we call that y, right? So x and y. You see where this is going? Right. So, yeah. So what do we know about this picture here? We have the base, the length is x, the height is y, and the length of the ladder is 25 feet. Now, the length of the ladder is fixed, right? It's a constant. I mean, yes, there are ladders that can expand and contract. You have, ladders with multiple parts to it that expand, but in this case, it's just a single ladder that is a constant 25 feet long. Okay, so what is the relationship between x and y here? Right, so how are x and y related? Sorry, these are e's related. So here's the answer, right? I'm just going to draw this again. This is a right angle. Why is it a right angle? We're assuming the wall is vertical, right? Usually when you have the side of a house, the wall is straight up and down. If you have a house that's leaning, that's probably not a good thing, right? So yeah, we're assuming that the ground is horizontal, the wall is vertical, so that makes this a 90-degree right angle. So what kind of triangle this is. This is a right triangle. And what do we know about right triangles? Right. Pythagorean theorem. In this case, instead of A, we'll use X. Instead of B, we'll use Y. And instead of C, we'll use 25. So this is really X squared plus Y squared equals 25 squared, which is 625, right? So X squared plus Y squared is 625 square feet. Right, so that answers my question, how are X and Y related? And this is how they're related, right? Okay. Now, if you were thinking of using like sines and cosines and trigonometry, notice that we're not told any information about these angles here. Right, so the angle between the wall and the ladder here, we can call that angle theta, right? And then, sine of theta would be x over 25, and cosine is y over 25, and so on. But we're not told that yet, right? That's going to come in part C. So for part A, we'll start with just part A, how fast is the top of the ladder moving? So in other words, what's the speed of this point up here at the top? So speed is the rate of change of distance, right? We want to find the rate of change of y. Okay, and that'll tell us the speed at the top. Right, what are we given? Well, we're given the speed, the horizontal speed, right, at the bottom of the ladder. Right, that's 2 feet per second. So what is that? That's the rate of change of x with respect to t. Right, so we are given that the derivative of x with respect to t is 2, specifically 2 feet per second, which is pretty fast, actually, if you think about it. Someone's, yanking the ladder pretty quickly away from the wall. But, yeah, 2 feet per second, right, for dx over dt. And part A says we want to find dy over dt, right? So how do we do that? Well, we take the equation that we just found using the Pythagorean theorem and take the derivative of both sides. We'll do this implicitly, of course. And this is one we've done several times already. We did this one earlier, I think, and we certainly did this in the previous video when we were talking about implicit differentiation, right? After all, this is also the equation of a circle, right? So here it is again, right? This is going to be the 2x times the derivative of x, right? Don't forget the chain rule, plus 2y times the derivative of y, also the chain rule. And then the derivative of 625 is 0 because 625 is a constant. Okay, so far? So what are we trying to solve for? We're trying to solve for the derivative of y. We're solving for this variable here. Okay, so that's just a little bit of algebra. Again, we'll subtract the 2x, x prime from both sides. Oh, instead of writing it x prime, I'll leave it as, dx over dt here. Right? So now we have 2y times the derivative of y is equal to negative 2x times the derivative of x. And now just divide by 2y. Cancel the 2's, cancel the y's. And finally we have that the derivative of y with respect to t is negative x over y times the derivative of x. With respect to t, that's supposed to be a t, right? And then that should answer the question. Now, of course, now we just plug in the numbers, right? And so in part A, I need this up here. So let's do part 1 of part A is x is 7 feet, right? So when x is 7 feet from the wall, or the ladder, the base of the ladder, the bottom of the ladder, 7 feet from the wall, right? So what's y then? Well, if x is 7, how do you find y? You go back to the Pythagorean theorem, right? So instead of x squared plus y squared equals 25, oh, sorry, 625. Oops. Now we know x is 7, and you solve for y. Okay, so subtract 49 from both sides. I think we get 576, right? And then when you take the square root, you get b. B is 24 feet. Okay, right, so we need that because when we want to find our derivative here, we need x and y. So we were given x, that's the 7 feet. Y we found is 24 feet. And the derivative of x, that was given. That was 2 feet per second, right? So times 2 feet per second. All right, now just do the math. Feet divided by feet, those units cancel. And then we just get negative, let's see, 7 over 12, I think, right? Negative 7 over 12 feet per second. Okay, so that's part A. Actually, that's only one part of part A, right? So they want us to do this for x equals 15. So part 2, x equals 15 feet. And then part 3, x equals 24 feet. And again, you're plugging in different numbers, right? You have to find y. And then plug in the same dx over dt, which is 2 feet per second. That was up here, right? So I think you can handle that. You're just plugging in different numbers here, right? And give you a little bit of a spoiler alert. If x is 15, y is also 15. And if x is 24, well, just reverse it. Y has to be 7 feet. So now you just plug in these numbers into the same equation here. So I think you can handle that. Right? So you should definitely do that, and I think you get 3 different answers here. Oh, so why is it negative? Right? Why is dy over dt negative? Right? And in some sense, the question is, how fast is the ladder going down the wall here? Right? Can I circle this? Right? So you see the down arrow over here? It's moving down. Well, that's why, right? Y is going up. Right? The bigger the y, the higher we are. So the lower the y, the smaller the y, the lower we are. So since the ladder is moving down, that's in the negative direction. So that's why dy over dt is negative. Right? When something is decreasing, when the height of the ladder is decreasing, the derivative will be negative. If something is increasing, like x is increasing, x is getting bigger, right, at a rate of 2 feet per second, but it's getting bigger, that means that it's increasing. And so the derivative will be a positive 2 feet per second. Make sense? Okay, so that's all just part A. I guess we should do part B. Consider the triangle formed by the side of the house. So that, again, that's this, sorry, I keep messing up. That's this triangle over here, right? Consider that triangle. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So, yeah, let's draw the picture again here. So this will be for part B. So here's the triangle, right? So remember, the length of the ladder is still 25 feet. The height of the ladder is y. The length of the ladder is x. Sorry, the height to the top of the ladder is x, and the length, the distance from the wall to the bottom of the ladder is x, right, which is 7. So we'll do this for x equals 7 feet. And as we know from the last one, y will be 24 feet, if we need that. But now we're looking for the area of the triangle. So what's the area of a triangle? Again, you should know that. You can look it up in the back of the book. It's 1/2 the base times the height. We did that earlier, right? In this case, the base is x, and the height is y. So instead of b and h, we'll think of this in terms of x and y now. So it's 1/2 x times y, right? So what are we looking for? Find the rate at which the area is changing. We want the rate of change of the area, right? So find the rate of change of area. So if you want the rate, we want the derivative. So take the derivative of a with respect to t. And again, I'll give you a minute to do this derivative here. Well, okay. So the 1/2 is a constant. That can come outside. And then we need to find the derivative of xy. And I certainly hope by now you're not doing the derivative of x times the derivative of y. X times y is a product. We need the product rule. Right? So first times the derivative of the second plus the second times the derivative of the first. Right? So, yep, this definitely needs the product rule. If you just do dx dt times dy over dt, well, you'll get the wrong answer, as always. All right, so now I think we can plug in the numbers. What do we know? We know x is 7, so that's 7 feet. The derivative of y with respect to t, well, actually, we found that in part A. That's the negative 7 over 12, right? So dy over dt is negative 7 over 12 feet per second, right? And then plus y is 24 feet. And then dx over dt, well, that was way up here, but that was given as well, right? That was 2 feet per second. So 2 feet per second. Okay. Well, we'll multiply by 1/2 later. This is going to be, let's see, negative 7 times 7, negative 49 over 12. And this is feet times feet, so this will be square feet per second. Again, that's because it's an area, right? Plus 24 times 2 is 48. Again, square feet per second. Okay, now we have a little bit of math to do here. 48 minus 49 over 12. Okay, so 48 times 12 is 576 minus 49 is 527. So what I get in the brackets here are 527 over 12. And again, this will be in square feet per second. And then when you divide that by 2, you get 527 over 24 square feet per second. And what is 527 divided by 24? Well, hang on. Can we simplify this? Can we divide by 3? No. Okay, then I don't think it can be simplified. Yep, okay. Then we just leave it as it is, or write it as a decimal, which is 21.95. So this will be approximately 21.95 square feet per second. That's the approximate. Actually, it's 21.958, so that 5 should really round up to a 6 if we're doing 2 decimal places, and I think we are. 21.96 square feet per second. Yeah, I'm not that picky. If you're off by, 1/100th of a square foot, it's not that big a deal. But that's part B, right? So that's how quickly the area is changing at that moment. All right, part C. Find the rate at which the angle between the ladder and the wall. Okay, so that was the angle I was referring to earlier, right? That's this theta here, up here. Okay. So find the rate of change of the angle, right, when the base is still 7 feet away from the wall, right? So I think we'll just do this again here for part C. Here's the triangle. Here's the ladder. Again, this is still 25. That's a constant. We can still call this x. This is y. And now what we're looking for is this angle in here. I'll call it theta. And what we really need, of course, is how quickly that angle is changing. So that's the rate of change of the angle, right? Rate of change is the derivative of theta. So what is the derivative of theta, right? Oh, when x is 7 feet. And of course, we know by now y is now 24 feet. So that's the question. How do we go about doing that? Well, again, remember, we know that the derivative of x is 2 feet per second. And we found in part A, the derivative of y is negative, is it 12 over 7 or 7 over 12? 7 over 12, I got it backwards. Okay, so negative 7 over 12 feet per second. Sorry, I'm in the triangle now. So, right, so this was given, this we found in part A. What we're looking for is the rate of change of the angle, right? So what we need is the relationship between the angle and either x or y, or both, right? So that's just the ratios of the sides of a triangle, right? So hopefully you remember SOHCAHTOA, sorry, T-O-A. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if this is the angle, right, then this is the opposite side, right? This is the adjacent side. And of course the 25 is the hypotenuse. That's the longest side. Okay. So it turns out it doesn't matter which one of these you want to use. Do you want to use sine or cosine or tangent? Doesn't matter to me. I like sine, right? So sine of theta is opposite, that's x, over the hypotenuse, that's 25. If you'd rather use cosine, then cosine will be the adjacent. The adjacent side is y, and the hypotenuse is 25. And if you insist on using tangent, although I wouldn't, tangent is opposite over adjacent, which would be x over y. And so that's why I would choose not to use the tangent. It's not negative, right? Because you got to use both x and y. Whereas if you use sine or cosine, you only need x or y, but not both. Okay. So yeah, so I'm just gonna use this one. It's probably the most convenient, right? And so that's the relationship between x and theta. Okay, so now how do we find the derivative of theta? Well, this is the equation. Take the derivative, right? Implicitly of both sides. Got it? Yep, so implicit differentiation, just take the derivative of both sides, and you would do the same thing if you chose to use cosine or tangent. But again, I prefer sine. So the derivative of sine we know is cosine. And the derivative of x over 25, well, right, you need the quotient rule? No, you don't need the quotient rule, right? 25 is a constant. So 1 over 25 comes outside. oops, sorry. Oh. So this is the derivative with respect to t. Oh, and I just realized I made a mistake here. Unintentionally, but now I realized I made a mistake. And so now this is just the derivative of x, which is dx over dt, right? So yeah, the right side is just 1 over 25 times the derivative of x. And now you see what I did wrong. Remember, what are we looking for here? We're looking for the derivative of theta. So if this is what we get, how do we find the derivative of theta? We can't. There is no derivative of theta. So that was the mistake I referred to earlier. The mistake was I forgot the chain rule. The chain rule says we have to multiply by the derivative of theta with respect to t, right? Because this is a t, not a theta here. Well, now it looks like a theta, so there's, right. So this is a t here. Remember, we're taking the derivative with respect to time. And that's true for all these problems. I think that was one of the first things I said, right? When you take the derivative, it's with respect to time, t. See that? So yeah, so this is all with respect to time. Okay. Well, so we're almost done. All we need to do is find the derivative of theta. So I can divide both sides by cosine of theta. Although, I mean, I guess I don't have to. I can plug it in. But yeah, divide by cosine theta here. And so the derivative of theta with respect to t will be what? 1 over 25 times the cosine of theta times the derivative of x. Right. And now we just plug in the numbers, right? Plug in the numbers. So the derivative of x with respect to t, that was the 2 feet per second, way up here. Yep. Oh, I wrote it down again here. There we go. So yeah, so this is, right, this dx over dt is just 2 feet per second. But what's theta? What's cosine of theta? Look at the triangle, right? Look at the triangle. So at this moment, right, here's the right angle. This is 25 for the hypotenuse. This is 7. And then this was 24 feet. So if this is our angle, cosine is adjacent over hypotenuse, right? So cosine of theta should be adjacent over hypotenuse. So cosine of theta will just be 24 over 25. So I'm running out of space. So that, we'll just plug all those numbers in, right? This is 1 over 25 times cosine of theta, remember, is 24 over 25. And that's convenient because 25s cancel. And then don't forget the dx over dt, that's equal to 2 feet per second. Right. So what do we get? We get a 2 on the top, a 24 on the bottom. So this is, oops, I didn't need a fraction that big. Yep, 2 over 24. Or 1 over 12. And yeah, forget the feet here. There is no feet per second. Yeah, my units are all messed up here. And the reason is because the 25, of course, is also a feet, is in feet here. So this would be, right, this would be feet divided by feet, which is just 1. So, yeah. So there is feet here, but then there's also 25 feet down here. And so, yeah, feet divided by feet is 1. Okay, so there's our answer, 1 over 12. But wait a minute, 1 over 12 what? So t is in seconds? Yeah, feet per second, seconds. What's the angle? What are the units of angles? So in some sense, angles don't have units. So you could just say 1 over 12, 1 over seconds. But we give it a name anyway, right? The unit for an angle is radians, right? Remember, angles are measured in radians. So this is 1/12 of a radian per second. Make sense? Yeah, again, if you forgot what radians are, remember an entire circle is 2 pi radians. If you prefer degrees, it's 360 degrees, right? So that means there's pi over 180 degrees radians per degree. So if you want to convert to degrees, you multiply by the reciprocal, 180 over pi radians. So if you insist on using degrees here, this is going to be 1 over 12 times 180 degrees divided by pi radians. And let's see, 18 over 12 is, I want to say 3 over 2. Yep, if you divide by 6. And so 30 over 2 is 15. So this will be 15 over pi degrees per second. And what's 15 divided by pi? It's about 4.77. So this will be approximately 4.77 degrees per second. Either way. So again, this is exact here, right? And of course, this is also exact. And this is approximate. I'm not picky. I'll accept any one of these. And I'm a little bit curious as to the book's answer, so let me look that up. Yep, the book seems to like radians per second. So the book's answer is 1/12 radian per second, which is probably what I would prefer too. But if you know, for you engineers out there, if you prefer degrees, great. 4.77 degrees per second is close enough, right? And you know, if you insist, you can convert that to minutes and seconds, right? But that's fine. I'm not going to do that. Anyways, that was a long one because there were 3 parts to this, right? A, B, and C, and we did all 3 parts. So I hope that's good enough. Okay, might as well do one more, and I'm picking number 29. This is also kind of a classic related rates problem, and it has to do with shadows. So you have a lamppost. Here's the picture on the right. You have a lamppost that's 15 feet above the ground, right? And you have somebody walking away from the light at a rate of 5 feet per second. And part A, when he's 10 feet from the base of the light, at what rate is the tip of his shadow moving? And part B, when he's 10 feet from the base of the light, at what rate is the length of the shadow moving? Okay, so this tiny picture here is a little confusing. So let me try to draw a better picture. Well, not a better picture, obviously. I can't draw a better picture, but a more detailed one at least. So here's the light up here, right? Here's the ground, right? And again, we know the light, here's the light, is 15 feet above the ground. So this is a constant 15 feet. Can't do this here. Yeah, let's just say that this is, right, 15 feet. There we go. And now you have somebody that's 6 feet tall. That's way taller than me, but that's okay. And let's see, 10 feet, so that's right about here. Draw my little stick figure. There we go. There's the guy walking this way at a rate of 5 feet per second. And the guy casts a shadow, so the light beam is going this way. And here is the tip of the shadow, right here. And what about the length of the shadow? Well, from the guy to the tip of the shadow, right, this here is the length of the shadow. So why don't we just call that L for length? All right, so that'll be L. And, well, we know how far the guy is from the base of the lamp. It's 10 feet. Right? Well, at that moment. Now notice the guy's actually walking this way, away from the light, right? So obviously the 10 feet is not a constant. So maybe we should, what should we call that? How about just x? So x will be the distance from the base of the light, the base of the lamppost, to the guy. Okay, and that's changing, right? So we're going to eventually do this at x is equal to 10 feet, but x is changing, right? And you can see what happens is that as the guy is walking this way, the tip of the shadow is also moving, right? So how quickly is the tip of the shadow moving? Well, what's the distance from the base of the light to the tip of the shadow? We can call that d if you want for distance, but it's just the distance from the light to the guy plus the length of the shadow. So it's just x plus L. It's just x plus L. And I shouldn't use d, should I? Because that reminds me of derivative. So can we come up with a better letter? S for shadow. I don't want to use S. How about capital D? That's fine. Although that symbol can also be used for derivative, but not in this case, right? Okay, so what are we trying to find here? At what rate is the tip of the shadow moving? So for part A, we want to find the rate of change of capital D. For part B, we want to find at what rate is the length of the shadow moving. So dl over dt. Okay, so those are the two questions. And in fact, they're very much related. If you know one, you know the other very quickly. So part A and part B are practically the same question almost. Okay, so yeah, what's going on here, right? This is another, you can see if I draw the light beam here, this is another triangle, right? And in fact, it is a right triangle. So you might think Pythagorean theorem. So why would we need the Pythagorean theorem? If we want to know the hypotenuse, the distance from the light to the tip of the shadow, that would be the hypotenuse. Let's call it 8. Oh no, H is for height. Okay, let's just call it B then. I'm running out of letters here. But we don't know anything about B. And in fact, that's not the question. The question has nothing to do with that distance. So why bother? We don't need that distance. Right? And so we don't need the Pythagorean theorem here. I mean, you can use it, sure, it's an option, but I don't think it's going to help you that much. We also don't know anything about the angles, right? We don't care about this angle. We don't care about this angle. Of course, they're related. They're complementary angles. So if you know one, you know the other. But again, we don't care what the rate of change of the angle is. We don't care what the angle is. That's not given in the problem. So again, you can use trigonometry if you want. You can use sine or tangent or whatever, but it's not necessary. So the picture is a little bit cluttered here. I'm going to draw a slightly better picture down here now. And I'm hoping this helps. Oop, it's not quite that bad. Okay, So this is the big triangle here. We can call this the green triangle, right? But notice there's also the guy. I'll just draw the guy as a stick here, right? And remember, the guy is what, 6 feet tall? So notice there's another triangle here. I'll call this the red triangle. Okay. So how are these two triangles related? Right, we have the green triangle. Should I draw it again? And then the little red triangle. So they're obviously not the same triangle. The green one's bigger than the red one. But notice all the angles are the same. This angle, right, is the same as this angle, and this angle is the same as this angle. So, yeah, so these are called similar triangles. When the angles of the triangles are the same, right, and these are both right angles here. That's a right angle, that's a right angle. We call them similar triangles. And what that means is, right, the ratios of the sides are the same. So let me draw the red triangle over here. And we know that let's see, the height, of course, is 6. And this, the length, is L. That's the length of the shadow, right? It's the same as the blue one in here, right? So here's the red triangle in the top picture here. Now I'm really messing it up, but, right? So what about the green triangle? The green triangle, the height is the light, the lamppost. It's 15 feet. And this distance here is what we call D, but remember, D is also x plus L, right? Because this distance here, this is your x. Okay, so similar triangles have proportional distances. So, right, so if I take D, if I take the ratio of D to L, I should get the ratio of 15 to 6. Right? And so if I multiply by L, I just get that D is 15 over 6 times L. Actually, hang on a second. 15 over 6. Right? If we divide by 3, we get 5 over 2. So that's even better. D is just 5 over 2 times L. Okay. So that's the relationship between D and L. Okay. And in fact, this also gives us the relationship between X and L, because remember, D was just X plus L. And if that's equal to 5 over 2 times L, when you subtract L from both sides, you get that X is just 3 over 2 times L. So that tells us the relationship between X and L. Okay, what are we looking for? We're looking for d over dt, d capital D, right, and dl over dt. So if this is, if this is d here, what's its derivative? There's probably a better way to do this, but yeah. I mean, what's the relationship between x and d then? Is that clear? Yeah, so x plus L is equal to D, which means x is just D minus L, right? And D was 5 over 2 times L minus L. Oh, but what's, oh gosh. We don't want this in terms of, yeah, we want the relationship between x and D, I guess. So what is L? L is equal to 2 over 5 times D, right? Okay, so this is D minus 2 over 5 times D, which is 3 over 5 times D. Right. And we didn't need this, but I think this probably makes it the most convenient. So x is 3 over 5 times D. So now take the derivative. Take the derivative of this. right? Do it down here. Take the derivative of x. That's just going to be 3 over 5 times the derivative of d. And we know what the derivative of x is. That was given, right? Remember what x is. X is the distance from the light to the guy. And we know the guy is walking at a rate of 5 feet per second. So dx over dt here is 5 feet per second. And so if you multiply by 5 over 3, the derivative of d is going to be, let's see, 5 over 3 times 5 feet per second. So that's 25 over 3 feet per second. So that's the answer to the first question. Capital D over dt is 25 over 3 feet per second. And now what about dl over dt? So now we can use this one, right? Take the derivative of x with respect to t. That's just going to be 3 over 2 times the derivative of L with respect to t. So that means the derivative of L is just 2 over 3 times the derivative of x. But once again, the derivative of x is 5 feet per second. So I'm running out of space here. This is going to be 10 over 3 feet per second, right? 2 times 5 divided by 3. So dl over dt is 10 over 3 feet per second. Got all that? Yep. So we didn't have to know anything about the angle. We didn't have to know anything about the hypotenuse. We just had to get, the key here is this relationship between D and L, right? It's the fact that when you have similar triangles, right, the ratios are proportional. So without this, we weren't going to get anywhere, right? This is what we needed to be able to get all these relationships between L, D, and X. Okay, so again, this was probably in the homework, but you can do number 30 instead. And it's a similar one, except the only difference is that we're reversing it, and the guy's walking backwards. He's walking towards the light instead of away from it. So then your derivatives might be negative because x is decreasing and so on. Okay. Yep, so this is, again, pretty standard, but the tricky thing is you have to know the relationships between similar triangles and that the sides are proportional here. Yep, because again, what's confusing is that a lot of people would look at the angles and use sines and cosines, or use the Pythagorean theorem. Again, all of that makes this actually even more difficult. I think the quickest way is just to use similar triangles here. So again, it's geometry, but it's stuff that you should remember from way back when. So I hope that helps. Okay. I think this will be the last one. And this is one from my notes. So I called it example 4, but I think we're way past number 4 already. This might be the 5th or 6th problem we did. Okay, so we have an inverted cone, so an upside down cone, which serves as a tank to store water. So there's water in the tank, right? The diameter is 12 feet, so the distance across is 12 feet. And the height is also 12 feet. You can see that here. Water is being poured in at a constant rate of 24 times pi cubic feet per hour. Okay, so what do we know, right? So we know that the diameter is 12 feet, which means, right, the radius, if you want the radius, that's going to be 6 feet. Okay, and what are we given here? Right, we're given that water is being poured in at a constant rate, so that means the volume of water is increasing at a rate of 24 times pi cubic feet per hour. Okay, so again, when you're given the rate, you're given the derivative. In this case, the derivative of the volume. right? So yeah, the water level is rising as we're filling this with more and more water, right? Which means the height is also rising, right? So the height is getting bigger. So what's the relationship between V and H? So the volume of the water here in terms of the height. Okay, so did you look that up? It's in the back of the book. This is essentially just the volume of a cone. So the volume of a cone is 1/3 times pi times r squared times h, where r is what? R is the radius, not of the cone, right? So it's not 6 feet. That's if we want to find the volume of the entire cone, of the tank the tank, then you would use r is equal to 6 and h is equal to 12, right? But the water has a smaller volume, right? This is the water that's in the tank, and that volume is changing. So the height is changing, and the radius is also changing, by the way. Okay, so yeah, so we need the relationship between the volume and h, and here it is, right? So we can now just take the derivative of the volume if you want. The volume being 1/3 times pi times r squared times h. The 1/3 and the pi are constants, so they can come outside. I'll just write it as pi over 3 if you prefer. And then we need to take the derivative of r squared times h. So how do you do that? Well, r and h are both variables here. So it's not 2r times h, right? Product rule. So first times the derivative of the second plus second times the derivative of the first, all times pi over 3. So yep, you get r squared times the derivative of h plus, and then h times 2r. So 2rh, but don't forget there's a chain rule here as well. So the derivative of r. Okay. So yep, that gets pretty complicated for the derivative. Okay, and I didn't have to do this, right? This was not necessary. What we needed here is the relationship between r and h. So how are r and h related? Okay, so maybe I should draw the picture a little bit better here. It's very hard to do a proper cone here. So this is h, and this is r. Right? If you consider the entire tank, right, r was 6 and h was 12. So r divided by h has to be 6 over 12, or 1/2. Right? Which means if you cross multiply, right, h is just 2 times r. Right? The height is twice the radius. That's true for the entire tank. It's true for the water, the cone of water at the bottom. Make sense? Sorry about that. Yeah, so that's how h and r are related. Right. Now, if you didn't know that, then it's just, you got to do this, right? You got to use the product rule and so on. But if we knew this here, we could have used that here actually, right? So here's what I'm thinking, right? Or better yet, for v itself, we can rewrite v, and I'm running out of space, so I'll have to do that down here. We can rewrite v the following way now, right? V is still pi over 3 times r squared times h, but we know what h is. H is just 2r. But I think, what do we know? We're looking for the rate of change of h. Right? So the question is to find how high, right, how fast is the water level rising? So the derivative of h. So we want this in terms of h, not r. So r then would be h divided by 2. So this will be pi over 3 times h divided by 2 squared times another h. And this is going to be pi over 3 times h squared over 4 times another h, which is going to be, let's see, pi times h cubed divided by 3 times 4 is 12. So this will give us the volume of water strictly as a function of h. Right. Now we can take the derivative of v, still with respect to t, right? In other words, we're going to use the chain rule here. We're going to take the derivative of v with respect to h times the derivative of h with respect to t. So the derivative of derivative of v with respect to h, so this is going to be 3 times pi h squared over 12 times the derivative of h. And 3 over 12 is just 1 over 4, so this is pi over 4 times h squared times the derivative of h. So that's what you would get eventually if you made that substitution here, of course. Eventually you would get this from all this mess up here. Okay. So, yeah. So little trick here. Once you get the relationship between r and h, then you get the relationship between v and h without having that pesky r, the radius, anywhere here, right? Okay. So what do we know? We know that the derivative of v with respect to t is this 24 pi. So all of this is equal to 24 pi. Right? Remember, that was the derivative of v. So we're solving for the derivative of h now. Sorry about that. So multiply by 4 over pi. Well, here, let's keep going. So let me write this again. So pi h squared over 4 times the derivative of h is equal to 24 pi over 1, right? So yeah, I was just going to multiply by the reciprocal here. We can multiply by 4 and divide by pi h squared. So do the same thing on the, that's not an h, that should be a 4, of course. Multiply by 4, divide by pi h squared, so that everything cancels on the left. And now we get the derivative of h. And this is going to be 24 times 4, which is 96. Notice the pi's cancel. Pi divided by pi is 1. So the denominator is just h squared. So there we go. That's the derivative of h. That's how quickly the water level is rising. And now we just want to plug in various values of h, 2, 6, and 10. So for part A, h is 2 feet, h is 6 feet, and h is 10 feet. So we get 3 different answers, just like the ladder problem had 3 different answers. So I think I'll do one of these and you do the others. Okay, so for 2 feet, the derivative of h is just 96 divided by 2 squared. So 96 divided by 4 is 24. Units. H is in feet. T is in seconds? No, hours. I'm sorry. T is in hours here. Very good. So 24 feet per hour. That's right. And now if h is 6, we get 96 divided by 6 squared. So 96 divided by 36. Calculator. 2 2/3, right? So that's 8 over 3 feet per hour. Right. Or if you just want to say 2.6 repeating feet per hour, that's fine too. I prefer the 8 over 3, but you know me, I'm not picky about that. And finally, when h is 10, we get 96 divided by 10 squared. So that's 96 over 100, or 0.96. Again, feet per hour. All right, there we go. And that was just part A. Part B, how long does it take for the tank to become full? So we're looking for how long does it take to fill up the entire tank until the whole tank is filled with water. Right, starting from empty, I'm assuming. Right, so we have a inverted cone. That's the tank of water, starting with no water at all. We start to fill it up. How long does it take to become full? Okay, got it. Well, so let's do this down here for part B. Right, we're looking for the time to fill the entire tank. Entire tank. Okay. So what do we know, right? Remember, we were given the rate of change of the volume was 24 pi cubic feet per hour. Yep, that was given in the problem. And what's the volume of the entire tank? So the volume of the tank, well, remember the tank is a cone, so it's 1/3 pi r squared h. For the entire tank, r is not 12 feet, that's the diameter. So r is 6 feet. So this will be pi over 3 times 6 feet squared. And then h is 12 feet. H is 12 feet. So putting this all together, we're going to get, let's see, 6 times 6 is 36, times 12 is 432. 432 divided by 3 is 144. 144 times pi. And then we have square feet times feet, that's cubic feet. Right, so that's the volume of the tank. Let's say the empty tank. Right? Well, how long does it take to fill the entire tank with water? Starting from empty, we're going from 0 to 144 times pi, right? Yeah, we don't need calculus for this at all, right? See, we're assuming that this rate here, that this is a constant rate. It doesn't depend on t. So every hour that goes by, we fill up 24 pi cubic feet of water every hour, right? So the question is, we multiply by how many hours, let's say t hours, to get the full tank of 144 pi cubic feet per cubic feet. See that? So 24 times pi times t is 144 pi. So just divide by 24 pi. And yep, I need a calculator even for that. 144 divided by 24 is 6. 6 what? 6, oh, t is in hours, right? So 6 hours. Right? So yep, it takes 6 hours to fill the entire tank. And that was part B. Time to fill the tank was 6 hours. Yep, it's really just the 144 divided by the 24. If you didn't see that right away. Okay, so again, this part B was really just an algebra problem. There's no calculus here, right? Because it's a constant rate, you know, it's like doing a speed problem, right? If the speed, let's say your speed is 18 miles per hour, right? And you go a distance of, let's say 54 miles. how many hours did it take to go that distance? Right? So you don't need calculus for this because speed is a constant, right? Speed times time equals distance. Right? So 18 times t is equal, sorry, that's not an x, that's a times. Just do it that way. Equals 54. So t is just 54 divided by 18, which I think is 3, if I did that right. Just double checking, yep. So in this case, it takes 3 hours to travel. Sorry, pen is a little jittery here. 3 hours to travel 54 miles if you're going 18 miles per hour. So that's the idea. It's the same idea as for volume and time and the rate of change of volume. Anyways, I hope that helps. So, yep, a lot of questions in the homework about related rates. Just do as many as you can. So you really want to get used to this idea of related rates. And it's, again, a lot of it is geometry, you know, the volume of a cone, similar triangles, Pythagorean theorem when you have triangles, right triangles, and all sorts of things. Trigonometry when you have to deal with angles and so on. So I hope that helps.